Hi folks, I am Marcus and this video is about automated traction control within the scope of planetary rovers. So it's inspired by this book here, but it's not limited to its contents. And for now I can already tell you that I will not bore you or torture you with too many or too complicated formulas. Instead, I think it's more meaningful to make you familiar with the topic and just to tell you what is to be considered, to give you an overview and so forth. And generally, why did I decide to discuss this particular topic? It's since, apart from aerospace applications, I consider myself to be an automotive guy. There are some similarities, and this leads, as you will see, to my first motivation. I mean, at the end of the intro, you already saw some kind of sneak peek of a rover drifting apart, or in better words, having a loss of traction. But of course, there is even more to show you. So here's an automotive example. You can see this car here, but it's trying to get it's in a very sandy environment. It's trying to get up a hill, and because of the sandy environment, because of the soil, I think it is comparable to planetary rovers because it's similar to what we can expect or what we can see on Moon or Mars and so forth. But before I say anything further, maybe just let's have a look. So as I said, it's trying to get up the hill. For now it's making progress. It has a translational movement, so to say, but now it's getting stuck. Almost no movement anymore, at least no real progress. Now it's turning back, but this is actually just cancelling the attempt because, this was not the goal. The goal was to get uphill, and it didn't make it, and this is obviously not good. And here we can also already see what traction control is about. It's about avoiding, the slip. What you just saw, it's about avoiding the loss of traction, and yes, why this is important we will also see in a few minutes. So, but as said, this is about planetary rovers. Maybe let's just have a look at another example which comes closer to this. I think you do know this vehicle. It's on the moon. The lunar, what's it called, vehicle? And but I'm not about this bouncing movement you just saw. I'm about this, what you can see in this last picture right here. So as you can see, here's again slip, and this is again not good. It's maybe not as bad as it was in the previous example over here, but still this is not efficient. It's very, it's more or less waste of energy. And however, let's have another example. Maybe you do know these kind of robots. These are so-called Volksbots, and we have some of these at the chair for robotics, and they're equipped with laser scanners and fancy stuff. They are for teaching purposes, not only, but also for teaching purposes. And I did record a brief video on my own. Maybe I'll just show you again. So you can see it's an aggressive movement, on purpose to be honest, but just to make it really clear. So here in slow motion, you can see once more that there is not 100% traction. So these were examples how it should not look like, but how should it look like then? And yes, I also did prepare something like that. So here, now it's actually a real rover, planetary rover, and you will see it is trying to get up this small but very slippy obstacle. And again, just let's have a look. This was very quick, so to say, regarding the traction control doing its thing. So maybe let's just have another look and try to focus on, the point when it actually hits the obstacle for the first time. I will comment on it. So watch, slip, and traction. As said, quite quick. So I think this is enough for motivation. Now I also want to give you some initial numbers and facts, not too many, but at least a few. And regarding this, if you think of Opportunity, the rover, Opportunity experienced a slip of almost or around 50% when it tried to get up a 15-degree slope. And 50% slippage is already quite bad. But on the other hand, Spirit experienced 100% slip, so there was no actual translational movement anymore at all. And this is the reason why the mission for Spirit was over, because then you can of course not do anything related to your actual mission anymore. No scientific work, no, actually nothing. So this is now also the reason, or this is the main reason wide traction control is so important, because if it fails, you can't lose your whole mission, and this is a worst case scenario. But on the other hand, Spirit, before this happened, experienced just 20% slip when it tried to get up a 90-degree slope, so you cannot simply say the steeper, the more slip you have. And also, just keep in mind, for the sake of completeness, that Spirit and Opportunity were identical. They were so to say twin rovers, and so it does not only depend on your rover, on your tires. They did not have tires in that sense, but it does not only depend on the wheels, but also, of course, on the soil and the specific environment and the specific situation your rover is in. And yeah, and I just wanted to show you yet another picture. Here you can see the trajectory. This part here is just zoomed in from this part, and I wanted you aware of this point here, this movement, because this looks so similar to the initial video we just saw with the car in the dunes. And here actually something similar happened, and it was trying back for a moment and then had another attempt to get uphill. Yes, and also Opportunity had an issue when it was stuck for 5 weeks, and it took the engineers 5 weeks to get it out of its let's call it trap. What are possible countermeasures? And I promised you not to torture you with too complicated formula, but a few easy ones, at least one easy one it shall be. So you can see S is for slippage, and it's a value between 0 and 1, it's just a percentage which we just saw for Opportunity and Spirit, and S dot is the derivation of this, so meaning, in other words, just the slip evolution. Let's have a look at the slip, so the first formula. There is a problem with this, so I can explain it maybe first. Here R is the radius of the wheel under consideration. This is supposed to be not in W and omega, so it's for the angular velocity of the specific wheel, and this here is the velocity of the overall system, so the rover. And yeah, what I just wanted to say, here is a problem with this equation, and I'm not about this part here that this could become 0 also, because this case is not important if it was 0. I mean, R cannot be 0. We have a constant radius different from 0, so this cannot be the problem. But the angular velocity, of course, could become 0, but this means your rover is standing, and this, in other words, means you do not have any slip, because, yeah, this does not make sense. This is not what I was about. I am about the overall velocity, which we do not know. Why do we not know it? Because if we have slip, we cannot just take the angular velocity, we have to do something else. And this is the part where it gets tricky. Well, so what can we do about this? I promised you to talk about countermeasures. Maybe you do know this rover here. If not, does not matter. It looks like a 8-wheeled robot, but indeed, it has nine wheels. So I'm talking about this additional one. And it's not just any wheel; it's a freewheeling wheel. What does this mean? So it is not connected to the drivetrain, so to say, of the robot. It does not experience any additional torque coming from the robot, and this is actually quite good to have this as a reference. So we can use this to get the more or less true velocity of the robot. Is this actually the case? Is the problem solved with that? Unfortunately, not really. This would have been too easy. With this technique, we still have a 10% error, especially during turning. So if we do a rotational movement, not a translational, but a rotational one, then of course you still can do your calculations to minimize the error, but still in practice, from what I've read, you still have this 10% error, and this is still too much, of course. Yeah, so what else can you do about it? For this, maybe you don't know what this is, what you can see in the picture right here. If not, I'll give you a hint if you can see it on my green screen. Here, it's just from a computer mouse. It's an optical computer mouse, to be precise. And with that, if you would put something similar on your robot, you can track the ground and again do your calculations, and then you do have your position, and from that, over the time, you can calculate your true velocity. This was actually implemented or built into a few robots, but you can easily see these are no practical planetary rovers, more or less prototypes, but yeah, actually it's just also for teaching purposes, not as cool as the one from my supervisor I just showed you before, but still there for, at least this one here at the right hand side is for teaching purposes. This one is a bit more enhanced, or a bit more, it's better, more or less, because it has 2 mice, and then you can to also reduce the error and so forth. But let's not focus on this. There are also other techniques, like visual odometry. You can use a camera for that, or here in this picture you can see a stereo camera, also again to be precise. Yeah, but visual odometry for getting your true position is yet another subchapter of the book, which is my main source and which I just showed you at the beginning. Yeah, and there are already videos from my fellow students also on this channel here on YouTube. So I would say check these out if you want to know more about this, and let's not dig deeper into this. Also, for the sake of completeness, again, you could use an IMU, an inertial measurement unit, to improve your data. And also, to be honest, in this book I just was talking about, they said they do not have good results with that because of the drift. But on the other hand, the guys here, how are they called? I hope you can see it. Yoshida, doesn't matter how they're pronounced. However, they said they do have actually quite good results with an IMU. So there are different opinions out there, let's put it like that. But just to mention, for example, Curiosity is also using an IMU, and it has not just one gyro or accelerometer, but 3 each. So again, for improving your data by having it in a redundant way. Yes, but for now, let us just assume that we have the true velocity, so to say. And yeah, what is then left to say? The suspension plays also a role, of course, on the attraction of the behavior of your system, but now in particular of your traction. And I think you maybe do know this suspension type, which is quite famous. And for that one, I found an algorithm which I love for its simplicity. And I will go through it step by step with you. And yeah, maybe let's just begin. So you have your initial speed, you're going straight with this robot, and you keep the speed, the velocity. Then, as an obstacle approaches the front wheels, you increase the speed of the middle wheel by 30% and decrease the speed of the rear wheel by also 30%. Then, when the obstacle is directly under the front wheel, again, return to your initial speed you had before. And after that, when the obstacle is close or next to the middle wheel, then again do some reduction, and here increase the speed of the rear wheel by 30%, as you can read it here. And after that, again, go to normal speed. So first direct, if it is going here to the right hand side, as it was just before in the GIF. If it reaches this point, you do this here. If it reaches this point, you do this here. And if it reaches the last pair of wheels, there's nothing special to consider anymore. This is why it's not mentioned here in the short description of this algorithm. And yeah, this seemed to be quite practical. And as said, I loved it for its simplicity. But what do you need for this? For this, you need some kind of sensors, like these load sensors. You can see it here separately, and here you can see it built in. Why do you need this? Well, how should you know when you reach your obstacle otherwise? And if you get this information from your load sensor, then you have to do your calculations or your control commands for the velocity really, really quick. But then this should work. Alright, let's continue before my video gets too long. I also want to show you some other approaches for control strategies. And let's maybe first have a look at a simulation which has no traction control at all. So this is how it goes. Trying to get up the hill. The goal is to reach the flag on the right hand side, and as you can see, it does not make it. Not really surprising if you have in mind that it has no traction control. Well, what can you do about this? You can use this approach called kinematic incompatibility. What is this? It's about the wheel fighting. So if you have a poor control, which is not considering that you have several wheels, and then this can lead to wheel fighting, so that they do not interact in a way which is good for your overall traction. And the first approach is considering this. How is it doing this? Maybe let's go a step back. It's using the angle. So if you have your suspension here, and if it goes uphill, then you have a specific angle here at this suspension, at this part. And this is considered for avoiding this wheel fighting. How does it look like then? So here's yet another video. Again, trying to get to this flag. And getting interesting. It made it. Very nice. Okay. Next, you can not only do what we just saw in this case here, you can also use, or you can estimate your slip. And it is done in this case by saying, hey, the slip has a constant coefficient. So yeah, it's fixed, it's constant. And before I explain any further, maybe just let's have a look. Again, have a look. And this is what happens. It does not make it. It looks even worse than what we have seen without any traction control. And this is again not surprising because, as I said, the slip is considered as a constant coefficient, and this is maybe just too far from reality, and this is why does it not work. But it is important still for the next examples, as you will see. So the third one is, it has a switching policy between the former two, so between this here and this here. It has a threshold, so if the contact angle of the wheel is below then use the first policy, and otherwise use the other policy. Let's again have a look. And it made it. So maybe it looks very similar to that one, and it's hard to see on the video, I know, but in the paper where I've got this from, the guy is called Gonzalez who made this, there is a movement in the direction out of the plane, so to say, if you love. So it's walking from the left to right, and this is coming, can I show it like this? In this direction, so to say, more than here before, so this is also worse than that one. So for the force, I go over here, and again, we have the question what to do about the previous disadvantages. For the next approach, we reuse the idea of the third control, which was here, but not only say if and else, but do the estimation for low slip, for medium slip, for much slip, etc. And then what we get looks like given here, over there in the bottom right corner. So far it looks good. And yes, it made it, and indeed, this was now the best version of all of the four. And yeah, alright, I think this was good enough for an overview. However, it's important to mention that all these approaches are velocity-based, and you can also do this in a torque-based manner, so to say, which may be more difficult, but it is advanced in comparison, definitely. And it's also actually used by, let's say, more expensive rovers. Anyway, I guess you have an idea now how to improve traction control step by step, and this brings us close to the end of my presentation, for which I have a last few words. So that is for the case that your traction control, or everything we discussed was for the case that your traction control works properly. I mean, that's what we are doing all the effort for. But what if it fails? What if, yeah, it fails no matter what you have tried, how hard you tried, what you considered, and what you have done? To answer what you do then, I have a final last video for you.
We want to check that the system does what it is supposed to do once on the moon. The Viper test unit that is behind me is a light version of the full Viper rover. We strip down the heavy components to try to maintain the mass load so that we can drive on Earth, which has a much higher gravity. And we need to do this because the system is designed to go to the moon, where it will be a lot lighter.
We have consulted NASA scientists who have analyzed images and data from previous Apollo missions to determine the distribution of rocks and craters of different sizes over certain areas of the terrain and the shapes and characteristics of rocks that we expect to see on the surface. So what we've done is use that information to recreate a moon-like terrain for the rover.
We're testing our rover capabilities when we go into an extreme sinkage environment. So on the moon, when we're roving, we might encounter areas with fluffier soil, something similar to quicksand. And so our rover has a capability to still make forward progress in these quicksands. We're also testing the ability that the rover has to move in a very special way. Is similar to a caterpillar inchworming motion. So the rover is able to change the distance between its wheels and apply power to the wheels in a very coordinated manner, and that would allow the Viper rover to get unstuck of this quicksand.
This is challenging for the rover, but it's important to test because we need to better understand and mitigate risks and hazards to the rover. And we have a great team of NASA engineers here to address any risks that we might face.